Hello friends, in this video I'd like to solve the following problem from the International Mathematical Olympiad 1992, problem number 2, which was proposed by India. We wish to find all functions f from the set of real numbers into itself such that f of x squared plus f of y equals y plus f squared of x for all real numbers x and y. It's a very nice functional equation. Here are my hints. First, set x to be 0 and justify that our function f must be a bijection, which allows us to find the unique number a such that f of a equals 0. And then you can try to find the exact value of this number a by setting first x to be a and y to be 0, and then the other way around, x to be 0 and y equals a. After you find a, try setting x to be 0 and y to be 0, and try to reduce our problem to Cauchy functional equation, and along the way show that f is odd. And remember this very basic fact from analysis, you can say, that if some function g satisfies Cauchy functional equation, that is g of x plus y equals g of x plus g of y for every x and y, and it is bounded from below on some non-degenerate interval pq, then our function must be linear. That is, g of x equals a times x for some constant a. We'll use this very fact. So give this problem a try, and I will see you in just a minute. Okay, alright, so as I suggested, let's maybe start by setting this equation to be asterisk, and let's set x to be 0. Then we have the following: f of y equals y plus f of 0 squared. And notice that the right hand side, this function, is bijective. Obviously, it's bijective, so that means that f composed with itself is bijective. But if f composed with itself is bijective, then f itself must be bijective. You can very easily verify that, or you can use the fact that if composition of two functions is bijective, then the inner function must be injective, and the outer function must be surjective, which means that f in this case is bijective. Alright, so there is one and only one real number a such that f of a equals 0. Yes, there is such because function is surjective. There is at most one because it's injective. And now let's set x to be 0 and let's set y to be a in our condition, in our very first functional equation asterisk. Then we have the following. F of 0 squared plus, well, maybe don't write it, f of a equals y is a, plus f squared of 0. But if you look closely, what is f of a? F of a is 0, so we have a equals f of 0 minus f squared of 0. Alright, and now let's set the other way around. Let's now set x to be a and y to be 0 in our condition asterisk. Then we have the following. So if x equals a, I have f of a squared plus f of 0 equals y plus f squared. Y is 0, so we have f squared of a, but f squared of a is 0, because it's 0 squared, and 0 is just f of a. And now let's pay attention. We have demonstrated that f of something equals f of something else. Our function is injective, so by injectivity of our function f, these two arguments must be actually the same. So f a squared plus f of 0 equals a. And now, if I mark this condition here square, by my condition square, I can replace a by f of 0 minus f squared of 0. So by condition which I marked square, we have the following. A f of 0 minus f squared of 0 squared plus f of 0 equals f of 0 minus f squared of 0. And now some cancellations. Here cancels with that. And we have the following. F of 0 minus f squared of 0 squared equals, pay attention, minus f squared of 0. And now we have an interesting situation, because the left-hand side, it's a square, is obviously non-negative, while on the right-hand side we have minus a square, so it's non-positive. The only possibility for that to be true is that both sides must be actually 0. Both sides must be 0. So in particular, f of 0 equals 0. Oh, all right, so now we know that f of 0 equals 0, and it is very, very important that actually this number a, yes, this number a is actually 0. Very nice. And using that, we can set some new things. Let's start with setting y to be 0 in our condition which I marked asterisk. Let's go back, let's see. I set y to be 0, so I have f of x squared plus f of 0. Maybe let's write it. Don't be too quick. F of x squared plus f of 0 equals, well, 0 f squared of x. But f of 0, as we know, it's just 0. So now we know that, maybe let's write it in green, for every real number x, f of x squared equals f squared of x, and in particular, for every, let's say, for every non-negative number x, f of x is also non-negative. Well, why is that? Because every number can be written as x squared, every non-negative number can be written as square of some number, and the right-hand side here is obviously square of something, so it's non-negative. i.e., maybe let's write it, i.e., our function f is bounded from below by 0 on the interval 0 plus infinity. We'll use that little fact later. Now, let's set something else. We have already set y to be 0. Now let's try setting x to be 0 in our very first functional equation. Then, what do we have then? Well, now we have f of y equals y plus f squared of 0. But f squared of 0 is 0, so f of y is y, i.e. f is involution. Our function is involution. Very well. And now, maybe let's write our very first functional equation, because we will work with it for now. It was exactly that. And maybe, you know what, I will mark these conditions. This condition I will mark, I don't know, triple asterisk. And this condition right here, I will mark double asterisk. Why not? Now, I will change y here and here to f of y. And I will change this to f of x squared. So let's change y to f of y. We have f of x squared plus f of, maybe let's write it in green, in yellow, f of y equals f of y plus f squared of x. And now, by my condition triple asterisk, this right here is just y. And by condition double asterisk, this is f of x square inside. By double asterisk, by triple asterisk. So we have f of x squared plus y equals f of x squared plus f of y. i.e., but notice that every non-negative number can be written as x squared, so we can write, we have established that for every real number y, and let's say for every non-negative number z, f of y plus z equals f of y plus f of z. It's almost Cauchy functional equation. Almost, but we are not yet there, because we need to show that this holds actually for every real z, not only for non-negative. But let's go maybe to where exactly? Oh, nowhere. let's set now, because this holds for every real number y. Let's set y to be minus z, and z is non-negative. In what we are setting it? In condition, let's say, triangle. In condition triangle. Then we have the following. F of 0 equals f of y, or f of minus z, plus f of z. But f of 0 is 0, so we have f of z equals minus f of minus z for every non-negative number z, which means that our function is odd. Yes? So let's write it. F is odd. Very well. And now I wish to extend my condition triangle to non-positive number z. So now let's set, maybe, or let is better word for now. So let y be arbitrary real number, and let z be non-positive. Then let's take a look. Let's take f of y plus z. Well, f of y plus z, by the fact that our function is odd, we can replace it by minus f of minus y minus z. But now z is non-negative. So by our functional equation triangle, we can replace it by minus f of minus y plus f of minus z. Yes? And now, using again the fact that our function is odd, minus f of minus y is f of y, and minus f of minus z is f of z. So we have now established that for every real number y and for every real number z, f of y plus z equals f of y plus f of z, i.e. f satisfies the Cauchy functional equation. And along the way, we have established that our function is bounded from below. It was condition which I marked. Have I marked it? No, but we have established it. So maybe let's write it. We have established that f is bounded from below on the interval 0 plus infinity. So it's very important moment. So f must be linear, i.e. f of x equals a times x for some real number a. And now we need to find value of a. Well, we can start by using the fact that f of x is x. We have the following. Well, a squared x equals x, and that holds for every x, so a squared must be equal 1. So we have only two options. Either a is 1 or minus 1. So we have only two functions to verify. So let's do verification. Let's start with our function f of x, which equals x. Or no, not even, because remember that our function, recall that f of x is non-negative for non-negative x's, so minus 1 cannot be, because our function then would be minus x. It cannot be. So a cannot be minus 1, i.e. a equals 1. So we have now only one function to be verified, and verification is straightforward. Verification is very straightforward. Left-hand side of our function, of our functional equation, is f of x squared plus f of y, and that is x squared plus y. And that this is exactly the same as y plus f squared of x, which is on the right-hand side. So the only solution of our equation, f is the identity of real numbers. And that closes our problem. It's a very nice functional equation, once again, from the International Mathematical Olympiad. Thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.